Hello everyone, and welcome back to the video series Deep Learning for Teens. In this video, I'll explain how an artificial neural network is trained. If you haven't already, I highly recommend watching the previous video in this series called ANN Building. In that video, I went over how to build a simple ANN for the MNIST dataset, and how to represent the ANN using TensorFlow code. In this video, I'll explain how to train a simple MNIST-like network similar to the one we developed in the previous video. To keep things simple, we will use a dataset where there are only 7 people and only 4 handwritten digits per person, 0 to 3. Since there are only 4 digits, we will need to modify our neural network to have 4 outputs instead of 10. Everything else about this network is the same as the last video. To train the network, we will first show it the number 3 from person 1. In its current state, the network thinks that the input image is a 2. As you can see, the neuron for the number 2 has an output of 0.7, which is higher than the output of all the other neurons. The output of the neuron for number 3 is 0.5, which is lower than the neuron for number 2. To fix this problem, we have to train the network. We do this by telling the network what the ideal outputs should be. In this case, the ideal outputs should be 1 for neuron 3, and all the other neurons should be 0. These ideal outputs should be the same as the labels for the input images. Based on the output of the current network and the expected outputs, the weights in the network are all updated. After updating the weights, you can see that the outputs are better, where the network now thinks that the input image is a 3 instead of a 2. To make this change, we might have to update the whole network many times. Now you can see with the corrected outputs, the network now thinks that the input image is a 3. Next, we train the network with the number 2 from person 1. Notice our labels have also changed to show this is the number 2. Now, we can train the network with the number 1 from person 1. The labels also changed this time. We continue training with the other numbers until we have used around 70 to 80% of the entire dataset. This part of the dataset is called the training set, because the network is trained with these images. In our case, the training set contains all the images for person 1, 2, 3, 4, and 5. We then take the images in the rest of the dataset to test how well the network can recognize these images. Since we are using these images to validate the network, we call these images the validation set. In our case, the validation set has all the images for persons 6 and 7. A very important thing to know about the validation set is that it does not update the network weights, unlike the training set. In other words, the network does not learn with the validation set. This means that the validation set is only used to test how well the network can recognize new images that it was not trained with. Whenever you are making a neural network, you need to split the dataset into a training set and a validation set. The network is trained with the training set, which means that the images in the training set are used to update the weights of the network. We then test it with the validation set. Since the network is never updated with the images in the validation set, if it can still recognize the images in the validation set, that means the network was trained well. Training the network with all the images in the training set is known as one epoch. Usually after one epoch of training, we test the network with all the images in the validation set. We usually need to show the images in the training set to the network multiple times before the network works well. In other words, we need to train the network for multiple epochs. To understand why we need multiple epochs, let's watch a video of the training of our ANN with the MNIST dataset. The progress bar is showing how much progress the ANN has made with training on one epoch, or one cycle of training. Since the code above specifies that we want 6 epochs of training, there will be 6 of these progress bars in total over time. Our first validation accuracy for the first epoch was 94.4%. And now, as you can see, our validation accuracy has increased from 94.4% on the first epoch to 95.8% on the second one. This is good, as it means our ANN is able to recognize images in the validation set. Our final validation accuracy is 97.4%, which is once again the accuracy that ANN gets when training with the validation set. Remember that we take our dataset and split it into a training set and a validation set. You can see from the TensorFlow training output that the training set accuracies are listed for each epoch. These go from 90% in the first epoch to 98% in the last epoch. The validation accuracies at the end of each epoch are also shown, and these range from 94% in the first epoch to 97% in the last epoch. This graph shows the training accuracies for each epoch. Notice that the y-axis is not 0 to 100%, but instead 89 to 99%. This allows us to zoom in and more easily see the changes in the accuracy. We usually plot both the training and the validation accuracies for ANNs. This graph on the right is identical to the graph on the left. The only change is that I changed the fractional accuracies to percentages. Thus, an accuracy of 0.97 on the left is 97% on the right. The final accuracy is the most important way to check how well the ANN works. In this case, the final accuracy of the validation plot is 97%, and so we say that our network is 97% accurate. In the next video, I will describe how to write TensorFlow code to develop and train ANN to learn MNIST.